So here we have a series of solutions that are made up from that blue food coloring, and let's take a look at Beer's Law as it relates to these solutions. So if we take a close look at these solutions, if I start all the way over here, well, that solution doesn't really look like it has much color at all. But as I move across, the color gets more and more and more intense as we go. That's because when I prepared these solutions, I prepared them by using more and more food coloring as I went across this series of 10 tubes. So the concentration increases, therefore the absorbance increases, therefore the intensity of the color increases. Now another thing that we can look at here is, again, even the dark tube isn't all that dark in this case, but these test tubes are only about a centimeter wide, so the path length for them is about a centimeter. What happens if we change that path length? Well, the easiest way to do that in these tubes is, instead of looking at them from the side where we've only got a path length of about 1 centimeter, why don't we look at them from above where our path length is now 3 or 4 centimeters. And you can see that even down here on the end where there's very little color, well, it's a lot easier to see that that's actually blue because we're looking through a much longer path length. And as I go again all the way over to the most concentrated sample, yeah, that blue color ends up getting pretty intense as we move down the row. So depending what we're trying to observe, depending what we really want to see, it's always important to keep in mind that the path length and the concentration both determine the color of a solution. Well, that's Beer's Law, and that's really how we need to think about solutions whenever we're dealing with a colored substance as part of any reaction that we do. It's always a good idea whenever you're observing color for whatever reason to keep Beer's Law in mind, because the absorbance of a sample, or the intensity of the color that we observe, is determined by the type of particles and how effectively each individual solute particle can absorb wavelengths of light. The path length, L, which tells us how far that photon has to travel through solution in order to get out and be observed on the other side. And the concentration of absorbing particles, C, which again gives us an idea of how likely it is that a photon is going to be able to pass through the solution we're observing. The other thing to keep in mind when we're looking at Beer's Law is that, what kind of an equation is this? Beer's Law is the equation of a line. So one of the ways we use Beer's Law fairly often is by collecting concentration absorbance data on a known sample or a known series of samples, using that concentration and absorbance data to generate a graph, and from that graph then determining the value of epsilon L, either combined as one term, or in some cases we can calculate it individually. So keep that in mind. Beer's Law tells us everything we need to know, usually, about colored solutions, and Beer's Law is really all about making a linear relationship between the concentration of a solution and the absorbance for that solution.